Hello there, and welcome back on our LabHub. So in this video, we're gonna talk about the gravitational pull of the Earth and the gravitational pulls at all, like the gravitational field. If talking about it more scientifically, and I forget about hello. So, no gravity estimated in one formula, right? In two formulas, it's mg, F equals mg. Well, now we really widely use it. And another thing is gravitational force equals to G times mass 1 times mass 2 divided by r squared, where G is a gravitational constant, and 1 is mass of one object, and 2 is mass of the next object, and the radius squared is distance between the centers of these two objects. So let's represent it. And the gravity for real is more topic to understand, not to calculate something. So let's draw the Earth and let's draw the moon. So what can we see here? We got a center of the Earth and we got a center of the moon. They attract each other with some force, right? So how can it be calculated? For instance, 10, mass of the Earth is 10, and mass of the moon, for instance, 1, right? So now we just need to paste the numbers in the equation, and we also need a distance. The distance between them is 5. So the gravitational constant is 6.67 times 10 and negative 11 times 1 times 10 divided by 5. Let's calculate it. And it's gotta be a lot. Yeah, it's gotta be a huge number. Approximately 1.334 e minus 10. And this is a large number because the masses are insane. The numbers are insane. The gravitational constant is literally 11 numbers after the dot. So in our case, this is a force of gravity between these two objects according to their radius between them, between their centers. Right? I mean centers and their masses. And with their force, they attract each other. Basically, the moon goes to the R side, right? So in that case, this is the Earth again, and this is the moon. The moon, yeah, it's orbiting around the Earth, but with some force, it goes on us because objects attract each other. And we'll break it down in more details in a video of relativity by relativity discovered by Albert Einstein. This is the more advanced representation of the gravity and the universe itself, and used mostly in astrophysics. When this thing, especially used in on-Earth technologies and like technologies around the Earth, like close to it, really close to it, maybe not going outside the solar system. And I already broke it down in the previous lessons. Just this is a more advanced understanding of it. And in addition, I want to say that even me and my microphone, since we got mass, according to Newton, we attract each other. And somewhere probably we will go to each other and face each other like that, and I'll be closer to my microphone, right? Yeah. Theoretically, yeah. But in practice, it doesn't work like that because we both attracted to the Earth. Yeah. So here's me staying on the Earth. My mass 80 kilos. When the mass of the Earth is a lot, all right? So I am just attracted to the center of the Earth. The Earth attracts me, and my weight here is approximately 800 newtons, right? So it's just uncomparable. We can't just say that I'm gonna attract some object by my gravitational field. No, just according to this, yes, everyone and every single object has a gravitational field around it. But when we compare it with the gravitational field we all attracted to, so the gravitational field of the Earth, it's just impossible to one object attract another while it's on the Earth. And even at all, the force will be too low because the gravitational constant has so many negative numbers. It's like so many zeros after the dot, right? So this is why we got a really small number, because we literally got 10 and 1 as masses and 5 as radius. So what I mean, yes, everyone has a gravitational pull, independent gravitational pull, and theoretically somewhere probably closer to the end of the universe, the object 1 with a mass of 10 kilos attract object 2 with 1 kilo mass if they were like 5 meters one another from. But it's in real conditions it's almost impossible, so it's only a theoretical thing. In real conditions, well, affected by the field of gravity, the field of the sun, there's effects on us too. Yeah, this is just for basic understanding of the gravitational universal law.